Well, howdy there, Internet people. It's Professor Leach again. Today, we're going to finish up the problem that we started yesterday and start talking about integration by substitution, our first major technique of integration. It's an anti-chain rule for those of you who like spoilers. If you don't like spoilers, man, you're in the wrong class. All right. So in this problem, we were told that the average value of the function 6 over x squared on the interval from 1 to c is equal to 1. So this is the equation that we're trying to solve for c. So we're going to set up this expression, the average value of 6 over x squared on the interval from 1 to c. And so for that, we integrate the function from 1 to c and then divide by the length of the interval. This is the continuous form of the average, finding the average, where we add things up and then divide by how much is there. So we're doing the same thing, just continuously. Later on, if I wanted to, or later on today, if I wanted to find the average of your quiz 3 grades, I would add up all your scores and then divide by the number of scores. I would add up the values for that quiz function and divide by the number of quizzes that were there. We're doing the same thing here, but just in a continuous fashion. We're thinking of integration as addition, so we're adding up all the values of the function. It's kind of a weird way to say it because it's varying continuously, and there it's not like a first and a second and a third and a fourth value. So we're doing this continuously, so it shows up as an integral, and then we're just dividing by the length of the interval. That's like dividing by the number of quizzes that are there. So, writing this statement into the equation gives us an equation with a definite integral in it. So we're going to use the fundamental theorem of calculus to get rid of this definite integral and just writes a function. Now that to do that, we need to read this function as 6x to the negative 2. So that's how I'm going to read this function. I'm going to read this as a 6x to the negative 2 dx, integral from 1 to c, 1 over c minus 1. Remember, c is what we're solving for. And this is all still equal to 1. So now I can take the find the antiderivative of 6x to the negative 2. It's just a power of x, so we'll add 1 to the exponents and divide by the new exponent. So 1 over c minus 1 is still there. The antiderivative of 6x to the negative 2 is we add 1 to the exponents and divide by the new exponent. And then we evaluate 6 to the negative minus 6 to the minus 1 from 1 to c. This is still part of an equation where all this stuff is equal to 1. Now we're going to plug in the endpoints. I forgot the x. That was close. So now into the x, I'm going to plug a c. I still have 1 over c minus 1. I haven't done anything with that, so there's no reason it should go away. And I'll have a negative 6 times a c to the negative 1. Minus a negative 6 times 1 to the negative 1. Plug in my endpoints. All this is still equal to 1. I wrote c and I forgot, and I should have written 1. Because I made a circle, and that circle looked too much like a C. I don't know if that's a more coffee problem or a less coffee problem, but I know what attempt I'm going to use. So we have now dropped the problem out of calculus. We've done all the calculus things to it. Now it's just an algebra problem. And it has lots of parentheses in it. And I'm missing one. Open, open, close, open, open, close, close, You can close that first one because all this stuff is being multiplied by 1 over c minus 1. So inside here, if I read this, I've got this 1 over c minus 1. I want to get rid of these negative exponents because we're playing the algebra game now. And I'm trying to solve for c. I don't want c to have negative exponents. I'm going to make a rational expression. So in the parentheses, I've got minus 6c to the negative 1. So that's minus 6 over c. I'm going to cancel these two negatives out to make a plus. And then it's 6 times 1 to the negative 1. So that's just 6. All this is still being multiplied by 1 over c minus 1. So now, I'm just going to simplify my expression in here. I'm going to get a common denominator with the 6 and the 6 minus c. And then I'll just divide that by the c minus 1. So if I add these two fractions, if I add those two fractions, this is going to be minus 6 over c plus 6c over c to get a common denominator. So it's going to be 6c minus 6 over c. That's what that fraction looks like. This is all still equal to 1. I'm carrying through a bunch of equations. Then we notice something interesting. So we see these c's down here, and we see a c up top, but we notice something interesting up top in that there is a common factor of 6 in the numerator. If I factor the 6 out of the numerator, that leaves behind a factor of c minus 1, and so we can cancel those out. We got to be careful that the thing that we're canceling, that we're not dividing by 0 when we cancel this out, but since we're looking at the interval from 1 to c, c is clearly going to have to be bigger than 1. So we're okay canceling these out. It's okay to cancel since c is not equal to 1. That's just because of how this interval is set up. If c is equal to 1, then the length of this interval is 0, and the average value of the function is not going to be 1. Also, we could see down here that c is not going to be equal to 1 because we're dividing by 1 over c minus 1. Can't divide by 0. So what we're looking at, after all this manipulation, our algebraic, our equation, is 6 over c is equal to 1. And that tells us that c is equal to 6. Any questions? This problem followed the same structure as the previous two problems. We set up an equation involving a definite integral, and we use the fundamental theorem of calculus to remove the definite integral part and get us to a nice equation. So we use the we set up an equation with a definite integral. That was our strategy, set up an equation. With a definite integral. And then, that was first, and then we remove the definite integral with the fundamental theorem of calculus. And then finally we have solve equation. All that to get us to an equation, just algebraic equation, we can solve it. Any questions?
Professor, is the fundamental theorem of calculus the 1 over c minus 1 times negative 6x to the negative first power evaluated from 1 to c? Or the...
Yeah, this is the step. This is the step where we use the fundamental theorem of calculus. 1 over c minus 1 is not part of the fundamental theorem of calculus.
But the evaluation.
The fundamental theorem of calculus is just find the antiderivative part.
Got it.
So
okay.
The fundamental theorem of calculus is that the integral from a to b of a derivative is capital F at B minus capital F at A.
Perfect. Thank you.
Which is the derivative of capital F.
So is the 1 over c minus 1 basically delta x?
No. 1 over c minus 1 is the length of the interval. That's from the formula for the average value of a function. So for an average, we add everything up and then divide by how much is there. So here we are adding things up, and then 1 over c minus 1 is divide by the length of the interval. That's how we want to think of the 1 over c minus 1. It says divide by the length of the interval. Because that's in this context, when you have, oops, I smeared my fundamental theorem. In this context, that's how we divide by the number of things. So if we wanted to find an average, if we have a discrete list of things and we want to find the average of, let's say, 10, 12, 12, 8, and 7, we would add up all those things, 10, 12, 12, 8, and 7, and then we would divide by the number of things that are there. In a continuous sum, here, this becomes a definite integral, and the 1 over 5 becomes divide by the length of the interval. In an average, a discrete average, it's divide by the number of items. We take the sum of the items and divide by the number of items. In a continuous sum, the sum of the items is an integral, and the number of items is the length of the interval. So the sum of the items becomes a definite integral, that's a continuous sum of the items. And then we divide by the length of the interval. So the 1 over c minus 1, that was the 1 over b minus a, that's us dividing by the length of the interval after we find the sum of the values of the function, but continuously. Any questions on problem 5? All right. Let's introduce a new thing by remembering an old thing. So continue working on the chapter 6 homework. That is our current business. Keep working on that. You have 4 quizzes now available. Quiz 4 is just finding antiderivatives. There will be, that was called Antiderivatives 1 or Indefinite Integrals 1. Anyway, there's going to be many of those because that's one of the skills that we want to have moving forward, finding antiderivatives. And that's what we want to continue working on today, finding antiderivatives. All right. So we start with the basics of finding antiderivatives. All the derivative rules that we know are now integrals that we know. Those are gonna be our baseline derivatives. Okay. So take a minute and load the program all of our baseline derivatives. So things like the integral of x to the n to x is 1 over n plus 1 x to the n plus 1 plus c for n not equal to -1. The integral of 1 over x to x is natural log of absolute value x plus c. The integral of e to the kx dx is 1 over k e to the kx plus c, and so on. So just keep all those baseline derivatives in mind, because what we want to do is start building on baseline derivatives. Oops, baseline antiderivatives. Yikes. I also start calling division multiplication. So it's just inverse multiplication. So I just keep saying it's just anti-multiplication. Why do we need all these extra words? It's because we developed the math rules after we developed the language for it. So that's why. Why do we keep asking questions of myself that I already know the answers? It's crazy. I need to find some new answers. I think I'm in a rut. So we want to continue finding antiderivatives. We're going to start with our baseline antiderivatives, add 1 to the exponent, divide by the new exponent. Or if it's 1 over x, the antiderivative is natural log of x. The integral of e to the kx dx is 1 over k e to the kx. The integral of sine of kx dx is -1 over k cosine of kx dx, or kx plus c, and so on. So this is the part of the ad for AM Gold. This is the one that says, and many more. And then we want to start looking at some rules or some techniques of integration. So we're going to start, once we have our baseline derivatives, we start adding techniques of integration. So once we have our baseline integrals, or in our case, once we're in the process of learning our baseline antiderivatives, we start adding techniques. Of integration. There are 2 major techniques of integration that we have to learn. These are the 2 big ones. The 2 big ones are integration by substitution. Integration by substitution being the anti-chain rule. So think of integration by substitution as the anti-chain rule. And the other technique that we're going to learn is integration by parts. Which is the anti-product rule. We don't need an anti-quotient rule because we don't really need a quotient rule to begin with, because we got the product rule and the chain rule, and we just combine those 2 things to create the quotient rule. It's handy when we're taking derivatives. It becomes less handy to have one for the inverse. So integration by substitution is the anti-chain rule, and integration by parts is the anti-product rule. After this, we get into kind of niche techniques. So then we just have to be, for integrals that don't fall into one of these categories, then we just have to be creative. So outside of the two big ones, it's everything else. So outside of these, we have everything else. So it's going to be combinations of things like substitution and parts. It's going to be combinations of those things and clever ways to make integrals fit into one of those categories. But it's just kind of everything else. A lot of algebraic sleight of hand, some trigonometric sleight of hand, and some, well, more algebraic sleight of hand. It just becomes make things fit into substitution and parts, or make things fit into our baseline antiderivatives that we already know. Any questions before we begin? Great. Let's talk about the most important one of all of our techniques of integration, and that will be integration by substitution. Good news is that we've already started doing this, but we haven't done all the technical details for it. We just kind of did it by feel. Integration by substitution showed up yesterday when we started doing, just to multiply by the 1 over k. Because it's the inverse, so instead of multiplying by the derivative of the inside, we could just divide by the derivative of the inside. And everybody was like, oh, everybody's on board with that. So we already have some kind of intuition built into this. That's what we want to notice here. There's already some intuition. And what math class is usually about is taking the intuition that you have, fixing it where it's broken, adding to it where it's lacking, and then using it as a base for doing more things. And that's really all you ever do in math class. So let's talk about integration by substitution. We know, or hopefully you believe me, that this is the anti-chain rule. So let's look at what we have when we're looking at the chain rule. So the chain rule, let's recall, the chain rule is for derivatives of compositions of functions. The chain rule is for the derivative of a composition of functions. That's where one function has been plugged into another function. So it's for taking the derivative of a composition of functions, and it's how we deal with one function plugged into another function. And then we write in general, we say that the derivative of a composition f of g of x, I'm going to highlight the inside function. So in this case, g of x is plugged into the f of x. we want to take the derivative of a composition of functions. And the chain rule says, take the derivative of the outside with respect to the inside. Then multiply by the derivative of the inside. And this is the chain rule. For example, if I wanted to take the derivative of a composition, let's suppose I want to take the derivative of the sine of x squared. So in this case, the outside function is sine and the inside function is x squared. We take the derivative of sine with respect to x squared. So the derivative of sine of something is cosine. But we take the derivative with respect to the inside, so we leave the inside alone. One of the common phrases that we get programmed with is take the derivative of the outside, leaving the inside alone. That's just a more operational way to say take the derivative of the outside with respect to the inside. And then we multiply by the derivative of the inside, which in this case will be 2x. Then, of course, we would put the 2x in front of the cosine because this looks terrible. It's like, oh my gosh, that looks terrible. Make the 2x the coefficient. And we're like, ah, much better. But here is how we use the chain rule. The game here is to be able to identify what's outside and what's inside. So for example, if I change the order of the composition here, I could write the expression sine squared of x. So in this case, it's the sine of x that has been squared. So here we're looking at the derivative of the inside function is sine x, and the outside function is squared. So to take the derivative here, once we identify the inside is sine x, we take the derivative of the outside with respect to the inside. The derivative of something squared is 2 times that thing to the first. Take the derivative of the outside, leaving the inside alone. And then we multiply by the derivative of the inside. Then we don't really write things to the first power, so we would clean it up. 2 sine x cosine x. Then if we want to flex on people, we would just write this as sine of 2x. And then people would be like, oh, where'd that come from? And then you'd be like, oh, trigonometry. Yeah. Any questions? So the chain rule and a couple of examples. Take the derivative of the outside, leaving the inside alone, then multiply by the derivative of the inside. Any questions?
Sorry, how come sine of x is now in parentheses squared?
Because that's what sine squared x means.
Ah, okay.
Find the sine of x first and then square the result.
Got it.
This is our common way of writing this expression. We probably should have just kept writing this, but it became less convenient. So somewhere along the way, we decided, I don't want to write all these stupid parentheses because I have to distinguish between the sine of x squared and the sine of x squared. So like, well, hey, let's say we're squaring the sine. And we all high-fived each other. It's like, well, yeah, that's awesome notation. I can't remember who came up with that because I wasn't there. But we all high-fived each other. And then until we started teaching it to other people, And they go, hang on a second. And so that's what happened there.
Got it. Thank you.
It's kind of like it. I think we have an advantage because we've been taught English, and English is such a mess of a language. It has all these weird rules. Like it's 1 goose and 5 geese, but it's 1 moose and 5 moose. And it's like, oh, come on, man. Oh, and then how we spell things. That's just a wreck. So especially if you come from a phonetic language. That's what I'm wondering. What happens if you come from a language where the written language makes sense because it's just entirely phonetic? Because there are some languages that you really can't have a spelling bee. It's just a pronunciation bee. If you can pronounce it, you can spell it. But English, you have to have like spelling bees. And they pick words that are spelled really badly. But we're just all agree that, oh, that's the correct way. It's almost like it was made to be difficult. Like we didn't want people to be able to do this learning thing. I'm sure that has nothing to do with it. So what we want to do is take our chain rule, since it's a rule for derivatives, and invert it into an integration rule. And we're going to call that integration by substitution. So we took the derivative of sine of x squared, and we got 2x cosine x squared. So let's write that down again on the next page. 3, page 3, so don't forget. So we know that the derivative of sine of x squared is 2x times the cosine of x squared. We want to look at this 2x. We want to remember that this is the derivative of the inside. That 2x is there because of the chain rule, and it's standing there because it's the derivative of the inside. We want to read this as x squared. X squared is the inside function. And then that 2x is there because the 2x is the derivative of the inside. The 2x is there because it's the derivative of the inside. And then cosine is the outside function. I'm just trying to use the common language that's used in a lot of different calculus classes. Cosine of the thing is the outside function. X squared is the inside. 2x showed up in the derivative because it's the derivative of the inside. That's the chain rule. So 2x is the derivative of the inside, and that's the chain rule. There's no comma. That's the chain rule shows up. So here's an expression that we wrote in terms of a derivative. We can turn all of our derivatives into integrals. Every time we write something down as a derivative now, we also get an integral out of it. So the integral of 2x cosine of x squared dx is going to be the sine of x squared plus c. All our derivative statements are also integral statements. Every time we write something down, we also get its inverse for free. Just like when we observe that 2 times 3 is equal to 6, that means also that 6 divided by 3 is equal to 2, and 6 divided by 2 is equal to 3. Those three equations are all connected. They all contain the same information. We can also see this plus c in action, because if I had sine of x squared plus any constant, when we took the derivative of that constant would be 0. All right. So here's what we want to identify. When we're doing an integration by substitution, we're going to use substitution when we can identify an inside function, and we also see the derivative of the inside in the thing that we're integrating as a factor. So for substitution, we're going to be looking for an inside function and a derivative of the inside. So for substitution, we'll be looking for an inside function, and we'll also be looking for a derivative of the inside. And then here is the function that we're actually going to be integrating. Once we identify an inside function and the derivative of the inside, then we're going to be we're going to find the function that's at the core of the integration. So then we're really integrating the outside function. This is all, the integral of a cosine is a sine. So when we have this derivative inside and the derivative of the inside, that's all just there to make the integral of cosine go. So if I look at a modification of this problem, if I want to integrate, say, leave a space, cosine of, let me change up the inside, like x to the third. If we want to make this just an, if the inside is x to the third, then to make this a substitution problem, we'll be looking for a derivative of the inside, 3x squared. So if we can identify a derivative of the inside and an inside function, in this case, our outside is still just a cosine. So in this case, we're still just integrating a cosine. The x cubed is messed up the inside, but the derivative of the inside is there as a factor. So we say, this derivative was found using the chain rule. We have to say the out loud. It's very distracting during the tests. But the x cubed and the x cubed inside and the 3x squared is a factor. That's what it tells us we're really just integrating the cosine. The integral of cosine is a sine. Now, the nice thing about these problems is we're claiming that the antiderivative of 3x squared cosine of x cubed is sine of x cubed dx. So if we take the derivative of sine of x cubed, we should end up back where we started. So we're claiming that this is our antiderivative. We can check. We want to check with the derivative. If we take the derivative of sine of x cubed, the derivative of sine of something is cosine of that thing times the derivative of the inside, which is 3x squared. We end up back where we started, so everything worked.
So in terms of writing it, like with f and g as the variables, it would be f prime of g plus c?
No, it would just be f, because we'd be integrating. In general, if we want to turn around our chain rule, the chain rule says the derivative of f of g of x is f prime of g of x times g prime of x. So if we integrate this one, if we integrate f prime of g of x times g prime of x, we end up with f of g of x plus c. So it would look like this. We want to integrate f prime of g of x the inside. We can only make this go if we've got also the derivative of the inside as a factor. So if we've got the inside and a derivative of the inside, then we're really just integrating f prime. And so the antiderivative is just f of g of x.
Thank you.
Oops, I wanted this whole thing in the box. I didn't want this separation here. So the thinking that we want to have is that I want to just integrate this outside function. This inside is messing things up. I want to just integrate the outside. To integrate and just ignore, essentially ignore what's going on in here, I need the derivative of the inside. If I've got the derivative of the inside, then I can just integrate the outside function. Any questions? Uh-oh.
Is it weird that to me, in my puny little brain, this is easier than the actual chain rule? This makes more sense to me than the chain rule does.
No, that's not unusual at all. So we also have, there's also a lot of stuff that goes along with the chain rule, because when we were learning the chain rule, it's like, oh, this is kind of a new thing. So you've got your chain rule eyes behind you, and I promise you that this will get much worse. That's not what you want to hear. Ignore that part. This will get much worse when it's not laid out as clearly for us. So, but don't worry, it gets much worse. But the other thing to keep in mind is, oh, no, that's actually not a thing that's related. I guess the short version of the story is I totally agree with you. Looking at substitution, it's much more obvious to me than looking at chain rule. I have that distinct memory as well. Thinking back to Calc 2, I'm like, oh man, why didn't they just talk about Calc when I was in Calc 1? Why didn't they just talk about it this way? And then because I looked at Calc 2 and it made more sense mechanically. The Riemann sum thing I never really got put together until like years after I had finished calculus and I had to start explaining the Riemann sum to somebody. That's the only time the Riemann sum really made sense. And I was sitting there tutoring a student when I'm like, oh yeah, this totally makes sense now. And the student was like, oh, what? I'm like, oh, nothing. Because at the time I thought the most important thing was to project perfect knowledge. And now I know that that's not really the case. You know what I mean? All right, so this is what we want to start working on, integration by substitution. We want to get to the point where we just observe things and integrate by substitution. Before we get to that point, we're gonna have to start breaking this down into pieces, and we're gonna have to build some kind of structure around it. Then we'll practice the structure, and then the structure will fade into the background. We wanna build a system so that we have something to fall back on, but as with all math classes, we want the systems to disappear into the background of our understanding. We don't want to think about the distributive property when I ask you to multiply something like 23 times 17. I want you to just multiply 23 times 17 in whatever way makes sense in your mind and come up with 391. I don't want you to actually have to write things down. I want you to integrate by substitution by looking at things, not having to do the system. Anyway, it's just a thought. Y'all have a good day.